Okay, so we are on. Welcome everybody, those on YouTube and everyone here right now. So this is an extra talk for the Abstract Mathematics 101 bootcamp. It came about because last time, in the last session, we covered the Zariski, the Hausdorff, Hausdorff topology, Hausdorff spaces. And we made a remark that, every metric space is a Hausdorff, and so non-Hausdorff spaces cannot be metrizable. So this triggered interesting conversation, people asking whether spaces that cannot be metrizable are useful. Yeah, and this talk is actually about that, to see even though it might not be useful in other subjects, mathematics can be useful to itself. So without further ado, I will hand over to Rakvi, who was very kind to come and give us a talk on Zariski topology. Thank you, Rakvi, and the floor is yours.
Okay, thanks Mambode for that introduction, and hi everyone. Some of you have met me before, but if you don't know me, I'm Rakvi. I'm currently a lecturer at UMain. Previously, I was a postdoc at UPenn. My research area is so far I've mostly worked in elliptic curves and algebraic geometry, so broadly number theory. And yeah, so today we are chatting about Zariski topology. So let me start with layout of how I planned this talk to be, and then let's see. So layout of this talk. So I planned this to be like a very first gentle introduction to Zariski topology. So first thing whenever we learn a new thing is just to discuss history a bit. When it showed up first in the literature, who introduced it, and so on and so forth. Second thing is, we'll actually see what is Zariski topology. So to have a not in wide generality, but to have a very uh, focused case and to see an example and how we define open sets in this kind of topology. So this is the second part. Third is, once we define the open sets and what they look like, to see some hands-on examples. And fourth part is, once we have seen Zariski topology a bit, to contrast it with or sort of compare it with what you're already familiar with, which is Hausdorff spaces or Hausdorff topology. Yeah, so this is roughly the plan of today's discussion. If there are any questions or anything I say is not clear, or if my voice is not clear, or if you cannot read something on the slide, please let me know immediately. And yeah, please feel free to unmute yourself and ask questions at any point. Okay, so any questions or any comments before we start?
Seems all good.
Okay, so let's start. So yeah, so this is a bit of history of Zariski topology. So actually, even I found out about this as I was preparing for this lecture last night. So actually, it was introduced by a mathematician named Oscar Zariski in 1944 in his paper that was titled it's a bit of a long title, but the only reason I'm giving you is in case you're curious and you want to explore this, you can check this out. The title is The Compactness of the Riemann manifold of an abstract field of algebraic functions. So this was the first instance in literature where this concept got introduced, and people realized that it is actually a very natural topology or construction if you want to study polynomials. So just a bit about Oscar Zariski. He was actually born in Russia, and then later he migrated to US in 1927, and he passed away in Brooklyn, or maybe Brookline, in Massachusetts, I think in 1986. So let's see what Zariski topology is and how do we define it. So this is definition / introduction of Zariski topology. So if you're familiar with fields, think of your favorite field. If you're not familiar with fields, don't have to worry. We can think of R, real numbers, and then take its Cartesian product, and that's going to be our space. Okay. And as you're familiar, as you have seen Hausdorff spaces, right? So there are two steps or two part of this structure of defining topology. First, you have a set, and then you sort of have a chart or sort of how do you want to define open sets on it, right? So this is our set. It's Cartesian product of our field n times, or just keep an example of real numbers in mind, Rn. So I'm not going to define open sets on it. I'm going to define closed sets on it, and which is equivalent because you know that open sets are basically complement of closed sets. So what are closed sets here? So this is how I'm going to define closed sets. So let me take S as set of, and this is any set of your choice. It can be finite, it can be infinite. There's no restriction. It just has to be set of polynomials in n variables with coefficients in field, or for a specific example, let's say R. So this is my, this I have not defined closed set yet. I'm in process of defining it. So let's just start with S, which is any set of polynomials in n variables with coefficients in R. And to this set, I can collect its zeros in this way. So let me call that V of S. So what is this? This is basically all the common zeros, or these are all the n tuples in Fn or Rn, whichever. Oh, let me not write this. This seems like quotient, so it might be confusing. Fn or Rn, whichever field you're thinking of. So these are all the n tuples such that you take any polynomial in S and it should vanish at A. Are these polynomials taking values in? It depends on how you want to think them. So for this, just for the definition, think of polynomials as rather formal expressions with coefficients in R. That's what we mean. As far as taking values go, actually, if you think about it, they can take value anywhere, right? I mean, it's just a matter of. So, just to take some specific example, this is just an aside. I'll delete it later because this is just to answer your question. I mean, if you think of this polynomial, let's say x plus y, okay? This is a polynomial in two variables. You can also think of them in more than two variables if you think of coefficient as being zero. Now, this has coefficient 1 and 1. So, this is, you can think of this in any field, right? Also, let's say particularly R. Now, the question is, where is this taking values? It depends on what values do you want to assign to x and y. If you want to think of them as real numbers, you can think of them as taking values in R, or complex numbers, or any field in general, right? Because all you're doing is you're adding them up. So they can take values in any set where addition makes sense, right? So where they take value really depends on how you are thinking of them or what your target codomain is. But just for defining Zariski topology, we can think of polynomials as rather formal expressions with coefficients in R. Is that okay, George? Did I answer your question?
Yes, thank you.
Okay, great. Okay, so this is what I do. I first take a set of polynomials and I collect all the common zeros. Okay, so these are all the tuples so that every polynomial vanishes for that. V of S are my closed sets. Okay. So the common zeros of polynomials is what I want my closed sets to be. So as you know, it's not just enough to give a set and call a bunch of things closed or open. We have to check that they also satisfy certain axioms of topology. But before that, before we check that it actually satisfies all the three axioms, here is a quick observation. If I start with a set and I take its V of S, that is same as first doing this I operation on S and then taking its V. I'll explain in a moment what I mean by I of S. And then this equality will also be clear. So what this thing is, this thing means ideal. And what does I of S actually mean? So that means take sums, and by sums I mean finite sums. Take finite sums and finite products of polynomials in S. So I'm starting with an arbitrary set, right? It's just a bunch of polynomials. To this, I do this I operation. So what I do is I take all the elements of S and I also collect their finite sums and finite products. So if I start with a single polynomial, if my set S only consists of a single polynomial, what sort of products can I take? I can not much really. Let's say I start with two of them. So what sort of elements will I have? I'll have F times G, I'll have F plus G, and so on and so forth. And you can obviously adjust constants in front, right? So like multiplying by a real number is obviously there. So this is what I mean by ideal. I want my sums and products to also be there. And now this equality makes sense, right? Because if you're collecting zeros, taking sums and products is not going to affect those. So ultimately the set V, which is all the common zeros, is same as what you originally had before, right? And there is an advantage of doing this. The reason is because when we'll be checking axioms of topology, this is one observation that we'll use. So this set is called an ideal. For those who are familiar with commutative algebra, it's completely okay if you're not, but in case you are familiar, ideal is a terminology that comes from there. It means precisely this, that your set is closed under taking products and finite sums. So we are doing that here. Okay, so let's proceed with checking that what we have defined here satisfies the three axioms of topology. So the first one is, so if we go by, I'm not sure if you have seen the like the open set version or the closed set version, but they are pretty much, I mean, it's not difficult to go from one to the other. So the first one says that your empty set and the full set should always be open. Or equivalently, if you take the complement, empty set and in this case Rn or Fn are closed sets. So let's check that these two are actually closed sets. So I should be able to find a set of polynomials such that empty set and Rn look like V of S. So let's, so I have Rn, so I have n variables, right? So let's label our variables. So suppose R, suppose R. Oh, we have shown that open and closed. Okay, yeah. Nice. So we are doing the closed set version of those axioms. So suppose our variables, let's label them something. Suppose our variables are x1 to xn. And to get empty set, let me do something really, really simple. So suppose I have x1 and I also throw in x1 minus 1. These two are polynomials, right? And if I want to collect zeros of them, so I want those tuples that are zeros for both of these polynomials. But the first polynomial tells me that x1 has to be 0. And the second polynomial tells me that x1 has to be 1. So there is no meeting ground here. So if you take V of S, has to be empty. Okay, so we get empty set this way. If you want to get Rn, so you want a polynomial such that everything is a 0 of that polynomial. So again, there is a very natural choice for it. Just take the 0 polynomial. Everything is a 0 of this, right? So if we take V of S of this, we get R of S. So we do get empty set and Rn in this. So these are closed. So let's go to our second axiom, which is, so the open set version is that arbitrary union of open set should be open. So when you take the closed set version of this, union becomes intersection because in complement, union and intersection sort of switch. So the second thing is that arbitrary intersection of closed sets is closed. And this word arbitrary, to sort of explain what it means technically, I mean, I'm not restricting myself to a finite intersection. I am talking about any sort of intersection possible. Like, I'm not even restricting myself to countably infinite or uncountably infinite or anything. Like, the number of closed sets sort of in my pack can be like arbitrary. So the indexing set can be whatever I want it to be. I'm not restricting it to be finite or any such thing. It's whatever intersection you want. So suppose we have an arbitrary intersection. So let's index them by something, let's say alpha or something. So I have all these closed sets and they look like V of S of something. And I'm taking intersection of them where alpha lies in my indexing set. Okay. Like if this is finite, you can think of this capital alpha as first n numbers or something like that. But yeah. So if I take intersection of V of S of alpha, I want this to be closed, right? That's what I want to show, that arbitrary intersection of closed sets is closed. So I want this to be V of something. And that something is what we have to find out. But let's focus on left-hand side for a minute or two. So what do I have here? So I'm starting with a bunch of zeros, right? And I'm taking their intersection. So what will I actually see? And I want something to be, I want those to be zeros of something, right? So one thing that you notice with this sort of topology is, so you start with a set of polynomials and you collect zeros of them. If you make that set bigger, if you put on more polynomials in your bag, the number of common zeros will decrease, right? Or at least, like at max, stay the same, but it will keep on decreasing, right? So here we have an intersection. So our set should be larger. Our set should be large enough, right? So what is the largest possible set that we can build out of the individual ones? If I give you two sets, how do we build bigger set out of those two things?
Union.
Union, yes. So this is what we do here. You take union of all these S alphas. And now you can see this should work out. Because if you put on union, what are the common zeros? It has to be zeros of both of them, right? So this is the intersection. And this is closed. So arbitrary intersection is closed. Let's go to third one. Third one is that finite union of closed sets is closed. So again, let's start with finite union of closed sets. So I have, let's say S1 to SR, and I take the union of the corresponding closed sets. And on this side, I again want it to be V of something. And this is not super obvious. This is not immediately obvious. Like, what should it be, right? I give you a bunch of zeros and I'm taking union of them. And I want you to give me a set of polynomials that realizes that as common zeros. So it's not obvious to think of this in general case. So let's think of it in a slightly simpler case. Suppose I give you two things. So suppose S1 is a single polynomial f, and suppose S2 is single polynomial g. And I ask you, linear combination is the keyword here. But there is another keyword missing. It's product. So linear combination and product. So let's see. So suppose we take f and g, these two single things, and I take zeros of f, and I also take zeros of g, and I take the union. Now, can you think of a polynomial that will have this union as its zeros?
F times G.
F times G, yes. So the zeros of F times G is basically where either F is 0 or G is 0. So precisely the union thing, right? So I'm taking product here. In other words, I'm taking the generators, and generators again sounds like a loaded word here, but really the elements that build S1. S1 here has a single element, F, so that has to be the generator. So I'm taking generators and I'm multiplying them, and that's how I get. So this is what we do in general as well. So, and this is where our observation from before comes in handy. So we know that V of S1 is same as V of this ideal S1. So if I throw in products and sums, I'm not changing my zero set. So I do this for every Si. And now this is a very, it's not obvious at all. It's a result that comes from commutative algebra. And it's called generators equivalent to monomials. Yes, in some sense, yes, you can think of them as monomials. Right. Like one way to generate them would be monomials. But we want finitely many generators. Potentially, if you just think of monomials, then you can get infinitely many of them, right? So, but here is a nice fact that it's Hilbert's basis theorem. So if we are thinking of R, and again this notation is it just basically what we have seen before. It's all polynomials in n variables with coefficients in R. So if we take any ideal in here, so any ideal in these multivariable polynomial set, any ideal in here is finitely generated. Which is a very powerful result, and it's completely non-obvious on how this follows or how this is proved, and we are not going to see a proof here because it requires like some terminology and machinery here, but this will really help us. So so now I have these, so I have finitely many SIs. I converted them to ideals, and now each ideal is finitely generated. Okay, so I collect generators for them. And basically, I do what we did for that baby case that we saw. We take the generators, we multiply them. And we'll do the same thing here, except that we can have more than two. So we'll also multiply and add them. So let's say I of S1 is generated by, let me call them F11 to F1 R1 something. And similarly, all of them have generators. So I of SR is generated by FR1, FR. Let me change the number here. Let me call it N1 or something. Or M1 rather. M1 to MR. So I have all these generators here. I just collect them. There are finitely many. And I take the ideal generated by all of them. So I take this big ideal that is generated by all of them. F1, 1, F1, M1, all the way up to. If my notation is a bit confusing or something, it just it's nothing complicated is going on here. Basically, I have finitely many ideals, and each ideal has finitely many generators. I'm just collecting all those generators and taking the ideal generated by that. And now if I take V of this should exactly be what we wanted. We wanted the union. So this should do the job for us. It's the same thing as what we did in baby case. When we have two of them and we want union, we take the product. When we have more, we can potentially take sums also. So it's basically what I'm doing. I'm just collecting the unions and products and sums. So. Finitely generated. Yes, it needs a bit of clarification, but basically what it means is that you have finitely many polynomials and everything in your ideal is built out of their products or their sums. So that's it. So let's see some examples on to get. So suppose we take n to be 1. Let's go to the simplest case, polynomials in one variable. So suppose we have R. Now what do closed sets look like in this sort of setting? So I'm taking, so my closed sets are zeros of a set of polynomials or a system of polynomials all in one variable. And as we know, again, this is a non-trivial sort of result to prove, but if I give you a polynomial in one variable, then it cannot have more number of roots than its degree, right? And to see all the roots, we don't even see them in R. To see all the roots, we have to go to complex numbers. But there are finitely many zeros. So a polynomial in one variable has finitely many roots. So if you take a system of polynomials and take its common zeros, obviously they will also be finitely many. So closed sets are finite sets, right? And any finite set you can think of, like, take a, basically you're taking finitely many real numbers, you can build a polynomial out of them that has all those numbers as their zeros. Empty set is also finite, yes. You can take two polynomials here that do not meet, so they will, right? So this set, in this sort of topology, which is the first thing that's stark in stark difference with Hausdorff topology, the open sets here are really, really huge. It's not so just to draw a picture real quick. So if this is our number line, in Hausdorff topology, our open sets, they look something like this, right? This is a perfect example of an open set. Like by perfect, I mean like a perfectly normal example. I'm not meaning to say that one open set is better than the other, but just this case. But in this topology, my closed sets cannot be this big, right? So the open sets are really, really, it's like you can just, so just to draw another copy of real line here, your closed sets are basically some finitely many holes. That's it. And everything that is remaining is your open set. So they're large, in fact, they're dense. So no worries about existence of roots. Yeah, I mean, so if I give you a degree n polynomial in one variable, you know it has n roots. but you might not see all those n roots in real numbers. You will see all those n roots when you go to complex numbers. So it can have no real roots, which is fine. Yeah. Why should additions come into play in more general case? Why not just for the multiplication? Each open set is dense. Yes, because you can see they're so huge. Yeah. Because you have, at worst, you have these finitely many holes, right? And you can always build a sequence that converges to this. So they are large, they are huge, in fact, they are dense. And this is one of the, we'll come to this when we'll discuss this versus Hausdorff topology. This is one of the reasons you cannot really put a metric on this. Because once you put a metric, you can always construct two balls that do not intersect. But here it's not possible. They are so large. They have to intersect. Oh, dense. I mean, again, not to go into mathematical details. Then sort of just think of it like it's everywhere. Like if you're more likely to run into something in open set than something in a closed set. That's what I mean. Like they are pretty much everywhere. Yeah, that's true, Mohammed. You can take multiplications. You can take multiplications, but the thing is, like what we saw before, right? Like having sums also do not affect the zeros. So you can take f times g times h, and all these things, and you can also include their sums. So that shouldn't, yeah, that doesn't affect the variety of the zeros. So in single variable, they are finitely many. In R2, right? Yep, distance is 0 means the points are same, but there is no notion of distance here. So in R2, these, so again, what are our closed sets? Are zeros of a system of polynomials. And by a system, it can have one or many, but not in one variable anymore. We are now in two variables. So now we no longer have finitely many sets. But again, the thing that open sets are dense, like open sets are huge, that is still here. So here are some examples of what closed sets look like. So I can take a polynomial like, let's say, x squared plus y squared equal to 1. And we all know what its solution set is. And what does it look like? Oops. Let me try to draw a better figure. Slightly better than before. Anyway, so this is one example of a closed set. Another example can be, so I can take something like x times y equal to 1. And this is, so in R2, like when we exceed our dimension, it's not necessarily finite. It can be infinite. But it can be finite also, right? We can always take, sort of expand our polynomials to make, drawing is a topological circle. Yes. Suppose you start with this. You can always throw in a line somewhere in your set And if you talk about its common zeros, you have these 2 points. So yeah, it's once we leave R, once we leave one dimension, there is no reason for this topology to have finite closed sets. They can be infinite. But again, the fact that open sets are really, really huge here and dense still remains. Because if you remove one circle or a bunch of lines or any sort of closed figure from R2, what you get is still it's large, it's huge. So yeah, since we already started talking about it, so let's sort of compare these two things, Hausdorff topology and Zariski topology. One fundamental difference that everyone notices is, of course, this that you cannot put a metric, right? So in Hausdorff topology, if I give you, let's say we are in R2, you can always find two balls that do not intersect. They're far from each other. And in fact, you can do this in any metric space, right? So suppose X is a metric space which has at least 2 points. If it has 1 point, then there isn't much going on for you to construct non-intersecting open sets. But suppose it has at least 2 distinct points. So suppose P1 and P2. So there is a notion of distance, right? So what you can do is, whatever the distance between them, we can always take half of that distance and sort of, or maybe even something smaller than that, and draw a ball around each one of them. To always get this, so at least one pair of non-intersecting open sets or open balls. This is a fundamental feature of metric spaces. But we cannot do that here in Hausdorff topology. Not always, not in general, right? So as an example, again, if we think of just R, so this is not always. Always is the keyword. Sometimes it is possible. So if we are, let's say you're not starting with R, let's say you start with a finite field. So there are finitely many points to begin with. So your open sets are also finite in size. So obviously you can construct a pair of open sets that do not intersect. They are finitely many points. But if you start with something like R or C, right? So this will not be possible. This is not always possible in Zariski topology. Because if we manage to find two open sets, say A complement and B complement, A and B being the corresponding closed sets, such that this intersection is empty, that means A union B is R. Now A and B are closed sets, and we know what these are, right? At max, A is of finite size. So when you take two finite sets and their union is R, it's not possible, right? They are too small. Exactly, because they are dense, they will always have non-empty intersection. Again, it depends. It depends on what kind of field are you starting with. As I said, if you start with a finite field, you can find open sets that do not intersect because they are going to be finite in size. But if you start with an infinite field, because they are dense, it's not possible. They are always going to intersect. So this is one sort of fundamental difference between them. But I would like to, I have some remaining time here. I would like to highlight a common connection between them. It's something that is more fundamental than the notion of distance that actually binds them rather than separating them. So this notion is actually one of my, I really like to think of Zariski topology via functions. So this is thinking of functions. So if you think of manifolds, or if you're thinking of metric spaces like Rn or any sort of thing, and you start thinking of manifolds, one way to think of manifolds is also via functions. So manifolds actually naturally arise as solution sets of system of equations, or if you want to think of them as rather graph of functions. And when I say equations and functions, obviously I'm not restricting myself to polynomials. Polynomials are a very special and a very concentrated examples of equations. But obviously we all are familiar that these things can be as general and as wide as it can be. And thinking this way has some very practical applications. Like, for example, so let me just say some practical applications. Is actually in CT scan. When we want to think of data that is in front of our eyes, or rather like the shape or the graph, so via coordinates. And many such things, like not just CT scan, like even our GPS coordinates and maps and stuff like that, right? So manifolds actually, and even when we define a manifold, or when we think of a manifold, the most interesting thing to do after that is basically to study functions from it. Because if we want to understand any set, the most natural way to do that is start looking at all the functions that arise from it. So it's like, let's say, or if you want to understand the target space, it's like throwing a lot of light on it, so throwing a lot of functions on it to see how it behaves or how it works. And when we think of like this, what are we doing in Zariski topology? Basically, we are restricting our focus just to polynomials. That's what we are doing. And in algebraic geometry, which is basically study of polynomials and its roots, by looking at it, like by putting some geometric structure on it, not just studying it through algebraic tools, we also want to study it through geometric tools. So Zariski topology is a very natural thing to consider. My functions, so whatever I'm interested in, is basically polynomials. So I take their common zeros, basically the system. I take the solution of system of a bunch of polynomials, and I call them closed sets, and it works. So now I start doing things with those. So one way, just to end, I'll give a very different example from what we saw before. Not very different. I mean, they are related, but it's not immediately obvious how the examples are related. But I just want to give this example to sort of highlight how we think of functions in Zariski topology. So so since my favorite subject is number theory, integers have to show up. So let's think about Z for a second. This is set of integers. And if you are familiar, if at all you are familiar, then a more general case to think would be R. But if you're not, it's perfectly fine. This is only for those who are familiar with rings and want to see a general version of this. Otherwise, don't look at right hand side, just focus on left hand side. You will not miss anything. So we have this at Z. Graph is same as subset of Cartesian. Exactly. Graph is basically a subset of Cartesian product. Right. To this, I associate this object or a set, whatever you want to call, spec of Z. So what is this? It consists of 0 and all these prime numbers. So 2, 3, 5, 7, 11, and so on. So if you think of number line, or if you think of, let's say, R, then I'm only looking at these. And what do these brackets mean? So when I say 2 bracket, I'm not just thinking of 2, but rather all the multiples of 2. Mod, yes, exactly, mod. Yeah, I'm thinking of all the multiples of 2. Okay, so I start with Z, I associate spec Z. And in general case, I have a ring. And I have something called spec of R. Whereas what is spec of R in general? This is basically set of all prime ideals of R. Again, just to repeat, if you're not familiar with this, then don't worry at all. It's only for those who are familiar and want to see a general version. Okay, so this is my set, like how I had Rn before. My spec of Z is now my set, and I'm going to define some topology on it. So let's see. So what's the topology? So what did I do before? I started with a set Rn, okay, and I started looking at polynomial functions, and I took a subset of that, right? So here I'm going to take a subset of Z, okay? So this should be your first hint that I'm in some way I'm thinking of my integers or my Z as functions or polynomial functions. So there is actually this is true. I mean, if you look at Z and set of all polynomials with coefficients in a field or R, they do have a lot of similarity. So this is, yeah, this is not coincidence. Yeah, spec in general, when you see it for the first time, you see it for commutative rings and also. So that's why I wanted to give a very specific example of integers. Okay. So you take any subset of integers, your favorite subset. It can be empty, non-empty, finite, infinite, whatever you want. And same as what we did before. So we take a subset of polynomials and we take the common zeros. So the same construction here. Okay. So I'm taking a bunch of integers, which I'm thinking as functions, which I'll explain later how it works out. And I take V of E. Now, what is V of E? It was common zeros before, right? But now here, it's a set of all prime ideals that contain E. Oh, it's same E as before. Okay. So as an example, if E is 6, just singleton 6, so what are all the prime ideals that contain 6? So I'm looking for all the primes such that 6 lies in this, right?
And 3.
Basically all the primes that divide 6. Exactly. So I have 2 and 3, right? So V of E is 2, and 3. And similarly, you can do this for any set, right? And these are my closed sets now. And again, you can check the way we did before that they satisfy all the 3 axioms of topology. So you will get empty set, you will get the complete thing, spec of Z, and it behaves well under arbitrary intersections and finite unions. So now how am I thinking of Z as functions? So this is where, so my set is spec of E, right? So take an integer of your choice, let's say any M or something. So I'm thinking of it as a function, right? So my domain is spec of Z, but my codomain is where things get a bit, I mean, it's slightly different from your usual notion of function. So when you think of function, you usually have a fixed domain and codomain in your head. But here, the situation changes a bit. So think of M as a function. M is an integer here. My domain is spec of Z, all right. So what happens? So I take a prime ideal. So I take some P. And what can I do? As Muhammad already pointed out, the operation is the clue here. It's mod, right? And when I have M and prime, what can I can do? You can look at M modulo P. This is my codomain. And now the reason I left this blank is because this is not a fixed codomain, right? It changes. It changes with every P actually. Codomain is range set containing image, right? But this is not something fixed here, right? It changes every time. In fact, when your P is 2, this is Z mod 2Z. When your P is 3, this is Z mod 3Z, and so on. So the notion of codomain is a bit blurry here. So let me leave it like a big question mark. But so this is how we think of. So in this setting of Zariski topology, basically your numbers, or let's say in general, the members of your ring, they become function themselves. And what's your domain? Your domain is now your prime ideal, or in this case, just the prime numbers. And you're looking at your number modulo P. So that becomes your codomain. So that's how your number is behaving like a function. And this is, again, this is not just a, I want to go like to dive into it a bit more conceptually. How is a function determined? So if I ask you, how do you describe a function? So basically, one way to describe a function is describe where it takes every member of domain to. So you take any member of domain. If you know how it is getting assigned, you know the function, right? So same here. If you have infinitely many primes, right? If I tell you that a number is, okay, a number is 0 modulo 2, 1 modulo 3, 2 modulo 5, and so on, you will know what the number is eventually, right? So an integer is uniquely determined modulo how it looks every prime, right? So that's the sort of analogy between, that's at least one common connection between manifolds or Hausdorff spaces and Zariski topology. It's like you think of them as functions, right? Except in Zariski topology, your functions are very concentrated and very, very focused. You're thinking of polynomials. But or like this, like members of your ring and so on. And Hausdorff topology or your manifolds, your functions are way more general than that. But ultimately, it's, yeah, the connecting dot is that you're looking at vanishing set of functions, and you define that as closed sets, and yeah, that becomes your building block. So yeah, so that's all I had. I think yeah, it's 1 hour, so I'll stop here. And if there are any questions or something to discuss, we can talk about it.
Thank you very much. Yeah, I've only made a few comments clarifying with respect to the topology that we've studied so far.
Yeah, I'm sure you will see these things as you progress later. But just to, like, not to get too technical, basically some things that I said, dense basically means very huge. Like dense is like you're like, if you are just walking randomly, you are very likely to bump into that open set than a closed set. So that's what dense means.
Yeah, we actually have the tools to define dense and boundary, but we haven't done it yet.
Sure. Yeah.
So just to explain dense sets. So a set is dense if its closure is the entire set. So if you've seen closures in topology, then all you have to know is that any set which closure is the entire set is dense.
Thank you.
Yep.
All right, I'm back. Yeah, I hope you enjoyed the session, Rakvi. Thank you so much for taking your time to walk people through. Can you hear me, everyone?
Yeah, I can hear you.
So yeah, I'll stop recording, and then maybe if you have 5 minutes or something, if people want to follow up, then yes.
Sure.
If not, we thank you for the amazing talk. Especially in the latter stages, to see the connection between the two, in particular the perspective, how to think this thing of the functions that you brought at the end was very.
Yeah.
I hope it gives you a hint.
Because I mean, before even I saw this, like this spec wasn't making much sense to me. Like when I saw it for the first time, I was like, why are we doing this? But then when I read it like that, like basically we are thinking of these as functions, so like everything made sense to me, because even in manifolds we ultimately care about what kind of functions are there. If there are not interesting functions to study from that space, it's not much of a use, right? So
yes, I was thinking that the indiscrete topology is too extreme.
That's true.
So the Zariski topology kind of sits in between. So it seems very cool.
Cool. So I'm glad you guys enjoyed it. And let me just stop recording just to make the video for those watching later shorter. And then Rakvi, if you have 5 minutes, if anyone wants